point O. Okay, that is our center of the circle. And then from here, we are going to draw a straight line. Okay, from here we're going to draw a straight line. The straight line has to go through the center of the circle and touches both ends of the circle. Okay, that's what you get. So any orientation, okay, don't follow me. You can do whatever you want, okay? Do any orientation. As an engineer from McMaster, one of the most important thing is that dare to become different. Okay, we have to do things different. Okay, then we will call one end point A. The other end is point B. Okay, where the straight line intersect the circle. Okay, then from here, we're going to pick a point. Okay, so we're going to pick a point over here. The point I'll pick is going to be a point C over here. Okay, so you see I pick a point, and this point is known as point C, right? Okay, if I'm going too fast, someone tell me please slow down. Okay, if not, I will proceed. So now we're going to construct lines now. Okay, the lines that we're going to construct is going to touch point A to point C, right? And then we're going to construct another set of lines from point C to point B, right? So what you realize that when we have done this, okay, what we realize is the angle ACB is 90 degrees. You will realize that. Okay, so the angle ACB is equal to 90 degrees. Okay, and this is not by chance. Okay, if we were to pick another point, okay, so let's say we were to pick another point, we're going to pick another point below the circle now. Okay, so let's say we're going to pick another point here now, or here. Okay, let's say we pick another point here. So I'm going to call this point point D. And if we were to do the same thing as before, at point A, we draw a line to point D. All right, from point D, we draw a line to point B. And once again, all right, you realize that this is 90 degrees. So that's how in the olden days they construct architecture with perfect arches. Okay, they produce architectures or buildings with perfect arches, right, by varying two lengths. Okay, so they can get a perfect arch. Okay, so you realize that the angle is 90 degrees at angle A, D, B. Okay, so what I want to do now is I want to draw your attention to the triangle ACB. Okay, I want to draw your attention to triangle ACB. So in triangle ACB, now I will join point C to point O. Okay, point C to point O. Then I'm going to define two angles. Okay, so the angle over here, angle OCB, I'm going to call alpha, and angle CBO, I'm also going to call, is also equal to alpha, not call, it's equal to alpha. Why is equal to alpha? Because both this distance over here are the radius of the circle. Okay, so R defines the radius of the circle. Okay, defines the radius of the circle, and we know the angle over here is equal to 2 alpha, because the angle in COB is equal to 180 minus by 2 alpha. Okay, so I'm going to use my protractor. Okay, so this is my protractor. I'm going to measure that angle alpha. So by looking, I'm eyeballing this. So my angle alpha is equal to is equal to 29 degrees. Okay, you can check later on. Okay, you can print my notes and check is 29 degrees. Okay, so the 2 alpha, okay, we're measuring now, it is about 58 degrees. In fact, it is spot on. Okay, Okay, it's spot. So this angle over here is 29 degrees. So this angle over here is 58 degrees. So this is the rules of the circle. And then later on, I'm going to teach you on a typical example how to use the rules of the circle to solve complex problem on Mohs circle. Okay, complex problem. Right. Okay. So this is rules of the circle. So that is why I need to use the one node. Okay, I cannot do this on the light board. If I can do it, I'm a freaking genius or a psychopath. Okay. So now let's look at normal stresses now. Let's look at normal stresses. Okay, I love this stuff. Okay, I hate manufacturing. Okay, I love this stuff. So normal stresses. So normal stresses. Okay, normal stresses or normal stress are stresses, okay, that are acting, right, perpendicular to the surface. Okay, so that is what normal stress are. Okay, so they're stresses acting normal to the surface. So I'm going to draw two things now. Okay, we're going to look at an element. So before we draw an element, we need to draw a transformation. Okay, so I'm going to construct our transformation. So in our transformation, this direction is x and this direction is y. Okay, so we are going to look at an element. So I'm going to write an element. Okay, so if we look at an element, it's basically a square. Okay, so this is what I call an element. Okay, now question for you guys. Can someone tell me what is an element in real life? Anyone? So I just drew for you an element. Okay, so what is an element in real life? Anyone? No answer at all? Okay.
Aluminum is an element.
Element.
Aluminum? I don't know.
No, it's not aluminum, okay? So yes?
Is it like a sensor?
Yeah, it can be a sensor. Yeah, absolutely right. So an element is like this, okay? So for example, you have a shaft. Okay, you have a shaft. Okay, I'm drawing a shaft now. All right. So your shaft, I'm going to draw the neutral axis. All right. So this is your shaft. So your shaft is going under a torsional load. Okay. So this is T in X direction. Okay, I'm going to call X. So if I call my top in X direction, so this is my X. Right. So this is my X direction. Then I'm going to call this will be my Y direction. All right. And then this is my Z direction. Okay. Right. So that is my top. Then also on this beam, we have an axial load compressing in PX. Right. And then on this shaft, we also have a bending a load in the Z direction. Okay, for example, we have a load in the Z direction. So an element is the location of interest where you position your sensor. I repeat again, is the location of the sensor where you is the position of the sensor where you are interested in what location. So we decided to put our element here. So this is our element. We decide to put our element there. Okay, we decide. So we stick our element there. But what is this sensor over here? So the element is made of multiple strain gauges. Okay, it's made of multiple strain gauges. So now if we were to take our element out and look at the plan view, okay, so now we look at the plan view. So this is our element. So based on that orientation that we, so I will call this that this is my X and this is my Y. So what we do with this element, if we put strain gauges. So this strain gauge will measure, right? Will measure strain in the X direction, right? Over here, we're going to measure strain in the Y direction. Okay, so all this that I've drawn are your strain gauges. Okay, and you can also put one, okay, in a different orientation, so you have strain in both X and Y direction. So that's what you're going to measure. Okay, so after you have measured the strain, you relate to the stresses, and then the outcome is you're going to see stress state acting on your element. Okay, so what do I mean by stress state acting on our element? So you will have our stress X, right? And then you will have our stress Y, right? So a very simple way to relate stress to strain, right? So a very basic formula is by using what? Hooke's law. Yes or no? Where stress is equal to Young's modulus multiplied by strain. Okay, so that's how we get our stresses. Okay, so now what we have drawn down here in stress X and stress Y are normal stresses. Okay, as I mentioned before, the normal stresses are perpendicular to the surface. So that is what we mean by perpendicular. Okay, so for this case, it's pointing away from the surface is positive, and when it's positive, when it's pointing away, it's positive, and this is what we call tensile. Okay, and then in the Y direction, it's also pulling away from the element, is also positive, and this is what we call tensile. Okay, now that is our element. Next, we're going to draw our Mohs circle. Okay, so we're going to draw a Mohs circle. Okay, we're going to construct a Mohs circle. So what I'll do is I need more space. Okay, so I'm going to move this a bit more to the side over here. Okay, you guys can still see it barely, I know. Okay, so for the first condition that we have seen down here, we declare that stress X is greater than stress Y. Okay, so next we're going to construct Mohs circle. So Mohs circle has two axes. Okay, Mohs circle has two axes. So the first axis that we see, so over here, this is your stress X, or stress, normal stress. Okay, so those of you who are taking 2P now, you will probably see this very briefly, very briefly in the last 2 weeks of your lecture, very briefly. Okay, I think I teach more detail here. Okay, because of time, it's not Dr. Koshi's fault. Okay, and then on the Y-axis, which I'm going to draw now, right? You guys can see Y-axis, and the Y-axis is the shear. Okay, x-axis is the normal stress, y-axis is the shearing stress. Okay, so it's the first time you've seen that sign, right? That sign. So this sign over here is your shearing stress.